I've always been fascinated by the idea of creating a world where life evolves on its own, not from carefully scripted behavior, but from random mutations and the brutal reality of survival of the fittest. In this video, I'm bringing that idea to life by giving each creature a unique brain powered by a neural network. Through countless generations of random mutations, we'll watch how evolution shapes their minds, how natural selection rewards the fittest, and how completely new behaviors emerge. It all stems from my fascination with evolution. About 3.5 billion years ago, life as we know it began with Luca, the last universal common ancestor, from which all organisms trace their origin. Over billions of years, evolution transformed that first single-celled life into extraordinary forms. From early microbes to the mighty dinosaurs that dominated Earth for millions of years. During that time, our ancestors was nothing more than a small, rat-like mammal, tiny enough to survive in a world ruled by giants. But then around 66 million years ago, everything changed. A massive asteroid struck Earth, collapsing ecosystems and wiping out the dinosaurs. In that sudden shift, mammals found new opportunities. From those survivors came incredible diversity. Our own early bipedal ancestors like Lucy, the woolly mammoth, the saber-toothed cat, and eventually humans. Now I want to create a timeline of my own, a world where life can emerge, adapt and evolve. And it all starts with this simple creature. I've named him Bob the Block. But of course you'll help me decide what he'll be called in the future. I've leapfrogged a few billion years of evolution and given him eyes. Since this project is built in Unity 3D, his vision comes from a set of raycasts that collect information about whatever objects they hit. The rules of my world are simple. Eat or die. A single day in this world lasts only 10 seconds. During that time, each creature must consume at least one piece of food to survive. Eating 2 foods grants survival and produces 1 offspring, and eating 3 or more foods produces 2 offspring. Like in nature, offspring inherit their parents' DNA, but random mutations may occur, some helpful, some harmful. In this project, mutations affect the creature's brain. The creature's brain is modeled as a multi-layer perceptron, a type of fully connected neural network with hidden layers. Each neuron's value is calculated by summing the weighted outputs of previous neurons and adding a bias. And the weights and the biases are the variables that evolve over generations, enabling creatures to adapt by, for example, moving more effectively toward food. The activation functions are functions you can use in order to keep a value in between a bound, for example 0 and 1 or -1 and 1, which we'll use for movement speed, as the creature can either move forward or backwards. Another example is rotation, where a rotation value of 1 equals a full 360 turn, while 0.5 equals a 180 turn. So the rotation is multiplied by a rotation speed factor, so the creature doesn't make a 360 turn in one frame, but rather over time, unless the creature decides to rotate in another direction in future frames. The inputs to the brain come from raycasts. Each raycast returns a 6-dimensional vector. Can the object move? Is it alive? How much health does it have left? And finally, the normalized x, y and z coordinates of the object, which are values between 0 and 1. If no object is hit, the raycast returns a 0 vector, still of 6 dimensions. Each creature fires 21 raycasts forward, giving 126 values for the input layer. In addition, we also add the creature's own normalized world position, so in total there are 129 input neurons. In addition to that, there are 2 hidden layers that each contain 32 neurons and an output layer of 2 neurons for speed and rotation. That means that there are 5,216 calculations per creature per frame. At 60 frames per second, that means a single creature requires almost 313,000 calculations per second. To speed things up, all calculations are GPU accelerated. However, the biggest performance cost comes from the raycasts, which must be recalculated every frame. With 1,000 creatures, there would be 21,000 raycasts per frame and over 5.2 million calculations per frame. This load would overwhelm the system and cause lag. So to solve this, I divide creatures into 8 groups, updating 1 group per frame. This reduces per frame calculations by a factor of 8, while still keeping the simulation stable and playable. To begin with, we randomly initialize the weights and the biases in the brain for the first Bobs that we spawn. Alright, so without further ado, let's do this. Okay Bob, survive and thrive. We of course need to spawn in a lot more agents, so we get a lot more unique brains that may be better suited to survive. Let's start with 300 agents. Well, that creature was off to a bad start. We see a lot of different behaviors. Some walk in a straight line, either forward or backwards, while others go in circles. As there is a lot of food, even walking backwards and randomly stumbling into food might be a good enough behavior in order to survive. Therefore, in order to encourage behavior based on knowledge of their surroundings, we slowly decrease the food in the world each day by less than 1%. That way, future generations may have gotten enough random mutations to actually get that desired behavior, since only agents with knowledge of their surroundings will be able to survive in an environment with little food. To the right, we follow the predictions made by the best performing creature in the previous day. We also see two neural networks. The one to the left is the ancestor's hidden layers and the ancestor's output layer, and to the right are the current creature's brain. The ancestor ID that you see on the top is the ID of one of the first 300 creatures that we spawned in. That way, we can track which creature any current creature originates from. The neurons are colored based on the summed weights and biases to visualize the difference between the ancestor and the current creature. Bright green neurons means the sum is very positive and bright red very negative. As a side experiment, I want to simulate what happens when an otherwise healthy population of creatures suddenly faces a drastic reduction in food availability. It's similar to what happened to the dinosaurs, who had no time to adapt to the abrupt changes in their environment. As expected, the creatures in this simulation also went extinct. In the separate world we were in before, I'll allow the creatures several thousand days to adapt before revisiting them to see how their population has progressed. Now let's reduce the food supply even further than in our first side experiment and see if our creatures can survive. It looks like two distinct species have emerged. One characterized by two bright green neurons in the output layer, and another with a red neuron dedicated to rotation. It will be fascinating to observe whether both species can withstand this sudden change. Interestingly, only one unique ancestor ID remains. This means that every creature from other ancestral lineages has gone extinct. Out of the original 300 creatures, only the descendants of a single origin have survived, while all others have been outcompeted. The results show that creatures with a negative neuron for rotation have outcompeted those with a positive neuron. The reason for this isn't immediately clear, but one possible explanation is that these creatures are simply better at avoiding one another. I'd be interested to hear your own thoughts in the comments. Looking at the broader dynamics, when the world is first initialized, there's an initial dip in population. This is due to creatures whose brains don't function effectively, for example those that fail to move. After this short decline, the population experiences a rapid boom. In a world overflowing with food, even moving around aimlessly or even backwards proves to be a successful survival strategy. As food availability decreases, so does the population, until it stabilizes once the reduction levels out. At this stage, movement towards food becomes essential for survival. The sharp drop you see in the food supply is a result of me manually lowering the amount of food in the world. This intervention caused a population decline and eventually led to the extinction of one of the two species. I also observed that even though some creatures were able to spot and move toward food, the sheer size of the world made it difficult for them to reach it in time. With less food available, they needed to travel much farther to survive. To address this, I increased the length of each day to 20 seconds. This adjustment gave the creatures more opportunities to find food, leading to another stabilization of the population. This graph shows the agent to food ratio over time. We can see that population stabilizes around 50 to 55%, which means there are approximately 2 food items available per agent in the world. This has been such a fun project to work on, and it's exciting to see creatures develop unique behaviors purely from random mutations, without any manual coding of their behavior at all. I hope you found this experiment as fascinating as I did. I'll be expanding the world even further in the future, with my next big goal being the introduction of predation. In the meantime, I'd love your help. What should I name this ecosystem, and what should we officially name Bob? Drop your suggestions in the comments. I'm looking forward to seeing your ideas. Thanks for watching, and I hope to see you in my next video.